Some circumstances require us to take the square root of a negative number. Now when we take the square root of something, we're trying to find a number that when we multiply it times itself will get us back to that number. So if I'm asked to take the square root of 25, I could say that my answer is 5, because 5 times 5 equals 25. We could also say that our answer is negative 5, because negative 5 times negative 5 equals positive 25. So either of those two answers would work for the square root of 25. But what happens if we're asked to take the square root of negative 25? Well, in terms of real numbers, there is no number that we could say that when we multiply it times itself will get us back to negative 25. Obviously, we've just said that 5 and negative 5, if we multiply those times themselves, will get us back to 25. There's no number, there's no real number that'll get us back to negative 25. So this was a problem that challenged mathematicians for an extremely long time. It felt like there should be a solution as to what the square root of a negative number should be. So this led to the creation of imaginary numbers in the imaginary unit I. And so what we have is that I, this lowercase I, is used to represent the square root of negative 1. And then therefore, if you square it, I squared, if we square both sides, we end up with negative 1. So the square and the square root cancel each other out. So here's an example of a number that when you square it, you end up with a negative answer instead of a positive. So this was the workaround that mathematicians determined. So for our purposes, we need to be able to simplify these types of numbers, so square roots of negatives. And so our approach is going to be to separate the square root of negative 1 from the number, change that into an I, and then simplify the rest of the number as we would normally if it was a positive underneath the square root symbol. So for example here, I'm going to separate it to square root of 16 times the square root of negative 1. We can separate that out since we know that if both numbers are underneath the square root symbol, we could just multiply them and combine them into 1. So we're just going the opposite direction. And so by doing this now, we can take the square root of 16, that's just going to be 4. And we don't need the plus or minus or anything like that because we're just taking a square root of a number. We're not taking the square root of both sides of an equation and therefore requiring that plus or minus. We're just going to put positive 4. And then we're going to swap out this root negative 1 with I. And so our simplified answer in this case is just 4i. For the second example, if we separate out the negative into its own square root, I'm going to have the square root of 27 times the square root of negative 1. And so now that square root of 27 I'm going to simplify as I would under normal circumstances. So I'm going to do my factor tree work here. So I've got 9 times 3. 9 is a perfect square, so I'm going to be able to take the square root of that number. So that's going to come out as a 3. This 3 here is still going to be trapped underneath the square root symbol. So I've got 3 root 3, and then over here I've got my root negative 1 that I separated out at the beginning. So I'm going to rewrite that as I. So it's very important that we make sure that that I does not look like it's underneath the square root symbol. It is not. It is a separate piece to our answer that's being multiplied by everything else, but it's not underneath the radical. For the last one, very similar to the one that we just did, I'm going to separate out the root negative 1 as my first step. So I've got that removed, so now I can work on my factor tree work here. I can go 4 times 11. Of course 4 is a perfect square, so that's going to come out as a 2. The 11 is trapped, so I've got 2 times the square root of 11, and then again I need my root negative 1 that I separated out to be represented by the lowercase I. So 2 root 11 times I. So essentially what we have are two distinct sets of numbers, real numbers and imaginary. The imaginary are what we just talked about, the square roots of negatives, real numbers, everything else. As long as there's no square root of a negative, it's considered a real number. Well, we can take those two number sets and combine them into what are called the set of complex numbers. And so a complex number is a number that has both a real part, A, and an imaginary part, something like B times I. And so scanning down the page, we can see that we're presented with a series of these complex numbers. Here's the real part, a, plus, here's the imaginary part, b times I, 5i. Here is the real part, 3, that's the a, and then negative 7i is our bi part. And so we can go ahead and do all sorts of operations on these types of numbers just like we would with a regular variable in there. So if it was an x instead of an I, we treat it exactly the same way. So in this case, if I'm adding these two numbers together, 8 plus 5i plus 3 minus 7i, these two complex numbers, I'm just going to treat this as a like terms exercise, gathering like terms. So I'm going to rewrite it without the parentheses so that we're not distracted by those. And so now I can see that my like terms, I've got these two real parts, so 8 plus 3, I'm going to get 11, and then I'm going to combine the imaginary parts. I've got 5i minus 7i, so I get negative 2i. Oops, let's try to rewrite that a little better. 2i. And so we're just gathering like terms is all we're doing when we're adding or subtracting a set of complex numbers. In the second example here, this time I have to distribute this negative since I'm subtracting that entire set of parentheses. So as I rewrite it without any parentheses, I've got 10 minus 4i, and then if I distribute that negative, I'm going to get minus 1, and then minus a negative I becomes plus I. And so now I'm in the same place that I was in the previous question, where I'm going to gather my like terms. So I've got 10 minus 1, it's going to give me 9. And then I've got negative 4i plus I is going to give me negative 3i.